Hi, welcome to the vpython video tutorial. My name is Eric Thompson and this is episode number 9. To view this source code for this program, go to my website vpython.ericthompson.com, scroll down to episode 9, click on the view code link, and there it is. Once you have the code, start up idle and open the code or paste it in there. In this episode, we're going to be looking at the force due to a spring, which is described by Hooke's law, and we're also going to be looking at dragging in the 3D space of vpython. So first, let me demonstrate the program. We have a weight attached to the end of a spring, and the other end of the spring is attached to a wall. This surface here is just a frictionless surface, and when we left click on the weight, we can go to the left to compress the spring or pull to the right to stretch the spring. And I have a little message up here that says springs have limitations, so if we pull too far, we're liable to, in real life, actually break the spring by deforming it. And going too far in real life, you can only go in so far, but in this program, it doesn't really have that limitation. So you can see we're actually going through the wall. But if you want a somewhat realistic result, you just try for around 35 centimeters or so, and then let go, and it'll go forever because there's no friction, and that's about how a spring will go. Some interesting things to notice about the motion of a spring. When the spring is at its relaxed length that it started out with, as it's oscillating back and forth, that's when the velocity is at its greatest, because we let it go over here, and then it speeds up, and then as it starts to compress, it slows down. So when it reaches the end point, the velocity is 0, and that's at both ends. Maybe hard to see because it's going kind of fast. And the force changes constantly. When it's in the middle at its relaxed length, the force, I believe, is at the greatest, but it's going so fast I'm not even sure right now. Okay, let's look at the formula for Hooke's law. Force is equal to the negative of a spring constant times spring displacement, and that's often written as F is equal to negative kx. K is different for every spring, and they manufacture springs to a certain spring constant. And x is the distance that it's stretched or compressed. In our case, we were stretched at 35 centimeters, so it was 0.35 meters. So we start off our program initializing the window here. I set the range to be 1 meter, centered in the 0, 0, 0. The relaxed length of the spring is important. I made it a pretty big spring, so 60.6 meters. That's like 60 centimeters. So So it's a fairly long spring. Yeah, it's a pretty big spring. And to draw the spring in vpython, we use the helix object. So the position is one end of the spring. Here I have it 75 centimeters to the left. The axis is equal to how long it is, so it's in its relaxed position it's only 60 centimeters. The radius of each circle in the helix is 10 centimeters. Coils, you can set this to whatever you want. That's just the number of turns. I made it 8. The thickness of each coil, I made it just 1 centimeter, and I gave it a color of green. Spring constant, you can play around with this. Different springs will have different constants. I gave this one a 2. Now the weight that's attached to the spring is a box object, and it's positioned at 0, 0, 0. And that's important to remember for this program because we're looking at the spring displacement, and we can easily detect it by looking at the position of the box. Because we started at 0 and it's attached to the spring, when the box moves 30 centimeters to the right, that means we've stretched the spring 30 centimeters to the right, so the spring displacement will be 30 centimeters. Likewise, if we push the box to the left 10 centimeters or so, that means that the spring displacement is negative 10 centimeters. So I gave the box a mass of 10 kilograms. Starts off 0, 0 for the velocity, acceleration, and the force. I drew a box for the surface. Really has no effect in our program because it's frictionless. The wall is also pretty much just for display purposes. It's not really doing anything. I just lined it up with the left end of the spring. I played around with these numbers to get it to work right. I created a label, drag weight to /n start. The /n just pushes the start to the next line. Now the code to drag, something I got from the vpython website documentation. Pretty much just copied it and modified it for this program. We have a loop that the program goes in. While the weight hasn't moved, that means it's really just going to look for mouse movements. And then it'll keep doing it until we let go of the mouse after we've moved the box. So detect the mouse events. To detect mouse events, we do this scene if scene.mouseEvents. We throw those into a mouse object. Then we have this if statement. If we've dragged the mouse and mouse.pick is equal to the weight, that means we've clicked on the weight and dragged. We're updating this variable to be wherever we dragged it. Pick is equal to mouse.pick. That's pick is really the weight object, so it's putting that into a variable as well. We're turning off the cursor. While you're testing programs, you might want to leave the cursor visible, because if the program crashes, you might see that the mouse is still invisible, and then you'll have to move your mouse up to the window before it's visible. That happened to me a few times in this program when I was testing it. Else if the mouse has been dropped, that event was detected in the mouse object. That means we're going to get out of this loop. We set this to none. There's probably no reason to set that to none because we're exiting the loop. But I suppose if you have another mouse event later in the program, it might be a good idea. And we turn the cursor back on. Wait move is equal to true. That just tells this to get out of the loop next time it goes through. If pick, that means we haven't exited the loop and we have clicked on the object. So we need to detect if we're at a new position, because if so, then we need to if the mouse is at a new position, we need to move the object. And we say new position is equal to scene.mouse.project normal is equal to 0, 0, 1. That confusing statement basically means that we're moving the mouse not really in 3 dimensions but 2 dimensions, and we've picked that we want to do the mouse to move in the X and Y directions. The Z, which is what the 1 here is perpendicular to the XY plane, and that's how we determine it. If we wanted to move in the XZ direction, the mouse to move in the XZ to our 3D view, we'd set the normal to be 0, 1, 0, because the Y direction would be perpendicular to the XZ plane. So you can play around with that, and actually, yeah, I'll do that later. Change that later. We can test that. So if the new position is not equal to the previous position, the drag position, then we're going to update it. Right here I said the mouse is moving on the XY plane, but really I'm only updating the X because I really don't want it to move up and down. So I've limited this to just the X's. Let me show you what happens if we take it off and run it. Now I can move the box up and down, and it's kind of interesting. I don't think a spring would go like this. I think it would deform in such a way, but the helix object doesn't look like that, so we get some interesting results. And I believe this motion may actually be valid according to Hooke's law. Of course, you couldn't go through a floor or anything, but if the floor wasn't there and you're in maybe outer space or something, and the spring wouldn't look quite that way, but that might be the motion that the box would move in. And since I took off those X, maybe I can try changing this to move in the XZ and see what happens. So now when I that was funny. I'm going to try that again. First I'm going to zoom out, see if I can see this. Okay, now you see instead of moving up, down, it's sort of moving. I can't move up anymore. I can only move in the X and Z directions. So get some interesting motion there. Alright, I'm going to change that back. And if we want to limit the user's ability to do impossible stuff, we can uncomment these lines. All it's saying is if I move too far to the left, set the x to be negative 0.35, and if I move too far to the right, set x to be 0.35. So now I'm trying to push left, I can't go any farther than that, and I'm trying to push right, but I can't go any further than that. So now it looks a little more realistic. And if you want to give this program to end users, you'd probably want to do something like that. But if you're just demonstrating it for yourself, I don't think you don't really need these kind of restrictions. So the spring displacement is equal to pick position, so that's the weight position. I described that earlier. It starts out at 0, 0, 0. If we move it a little bit, then that is our displacement. Our spring's axis is going to be whatever length it started out with plus the displacement. I have pick position, which is the same thing, but to be a little more accurate or a little more readable, I'll write that. The drag position is equal to the new position, so I believe this statement is what actually moves the box. This one moved the length of the spring on the screen, and I'm pretty sure this is what moves the box on the screen. Here, this is just a message to the user. So once we let go of the weight, I'm again looking at the spring displacement and updating the axis in case it didn't happen last time, although I believe it did. Those two lines might not be necessary. Setting finished is equal to false because we're going to go through our loop while we're not finished. Actually, I never set it to true, so it's an infinite loop. Difference in time, 0.01 seconds. This is the total seconds, 0. Rate, 100. We don't want to go through the loop more than 100 times a second. First, we calculate the spring force using Hooke's law. Spring force is equal to negative times the spring constant times the spring displacement. That force acts on the weight that's attached to it. It's at the end of the spring. So the weight dot force is equal to the spring force. And from there, we simply use what we've used in many previous programs. That's Newton's second law. Force is equal to mass times acceleration. Solving for acceleration. And then using the position equations to get the velocity and the new position of the weight. So those should be looking very familiar to you by now. The spring displacement is equal to the weight position. We're just so this moved the weight. Now we're gonna stretch or relax the spring, however much the new displacement is. And then we finally have a message to the user showing some statistics, the velocity, acceleration, and force. So this one was pretty easy, and that's Hooke's law. Alright, thank you for watching, and I'll see you next time. Bye.